We'll continue our discussion of inverse matrices with the idea of elementary matrices. Elementary matrices are matrices that are formed by performing a single row operation on the identity matrix. Here's an example where I took the 2 by 2 identity matrix and multiplied the first row by 3. Here's one where I started with the 3 by 3 identity matrix and I did 4 row 2 plus row 3. And here's a 4 by 4 example of an elementary matrix where I switched rows 2 and row 4. Elementary matrices are going to be very helpful in us finding our inverse matrices. Elementary matrices are very important for finding the inverse of a matrix. But before we discuss the importance of these, let's look at a few theorems and a few ideas from these. Let's suppose we have an elementary matrix E that's obtained by performing a certain row operation on I sub m. So we have an m by m identity matrix and we perform some operation to get my elementary matrix E. We're also going to suppose that A is an m by n matrix. Then the product EA is the same matrix obtained by performing this row operation on A. So multiplying by an elementary matrix on the left is the same as just performing that row operation on that matrix A. While I won't prove this directly, I do highly recommend that you try out a few examples and try to convince yourself that this is true. One of our other big properties is that every elementary matrix is invertible, and its inverse is also an elementary matrix. While I also won't formally prove this one, the idea is that every row operation is reversible, and the inverse of an elementary matrix is the elementary matrix that results from that inverse operation. So the idea is just that we're going to undo the row operation with another row operation. My next big result says that every m by n matrix A can be decomposed as a product of elementary matrices and the reduced row echelon form of A, which we'll denote by R. So this means I can write A as E1, E2, etc., all the way up to E sub P times R, where all of these E's are elementary matrices and R is the reduced row echelon form of A. And we will prove this one. Since R is the reduced row echelon form, we know that A can be reduced to R by a series of row operations. Since we know that every row operation corresponds to an elementary matrix, and multiplying an elementary matrix by A is the same as performing that row operation, I can write this as F sub P minus 1, etc., all the way up to F2, F1 times A is equal to R, where these F's are my elementary row operations that correspond to the row reduction to get from A to R. Since we know that every elementary matrix has an inverse, we can multiply both sides by the correct sequence of inverses to get that A is equal to F1 inverse, F2 inverse, etc., all the way up to F sub P inverse times R. And since the inverse of an elementary matrix is also an elementary matrix, I can rewrite these as A is equal to E1, E2, etc., all the way up to EP times R, which gives me the result. Our next result says that if we have an n by n invertible matrix A, then the reduced row echelon form R of A is the identity matrix, and A can be decomposed as the product of elementary matrices. The fact that the reduced row echelon form is the identity matrix is something that I will prove in a later video, but for now I'm going to talk about the second part of this, that A can be decomposed as a product of elementary matrices. Our last theorem said that we could write A as a product of elementary matrices and the reduced row echelon form, so we have that A is equal to E1, E2, etc., all the way up to EP times R. Since the reduced row echelon form is the identity matrix, I can substitute I in for R. And since multiplying by I doesn't actually change anything, I then have the result.